Hello everyone, welcome back. This is video 2, logarithmic and exponential integration. In the previous section we covered the power rule. In the power rule we saw that the integral of x to the n dx is equal to x of n plus 1 over n plus 1, and we have to add the constant c, but we had a restriction where that n cannot be equal to 1. What is that? It's because if n is equal to 1, such we can see in this case 1 over x, where the exponential would be 1, right? With no exponential, but with exponent would be 1. This would be x to the negative 1, but then the denominator would be 0, so our answer would be undefined. So the power rule cannot, cannot be applied here. To get around this, we have a different rule, which is the logarithmic rule, which allows us and tells us that the integral of 1 over x dx is equal to the natural log of the absolute value of x plus a constant c. Now, let's do an example. Just to reiterate that the antiderivative of 1 over x is the natural log of the absolute value of x, not just ln of x. Okay, we need to make sure we include the absolute value. And it's there because ln of x is only defined for positive x. But 1 over x exists for all of x that are not equal to 0. In most applications, you'll see x will be positive, but keep the absolute value bars just to be safe, especially on your exam. Okay, so let's work through an example. So let's say we have the integral of 5 over t dt. How do we apply this? In this case, our x is t, so this is equal to the natural log of the absolute value of t, right, plus c. But notice that I'm forgetting something right here, that you still have to put the constant out before I could pull the constant out, so this is 5. Why is that? It's because I could have done this, I could have written this if I wanted to, just to make it look exactly the same. I could have written this integral 5 over t dt as 5 over the integral 1 over t. The constants can be pulled out. So this right here is 5, the natural log of t plus c. Same thing, okay? So below the 3 in front. Now let's look at another one. So let's say you have something like 1 over 3 x dx, very similar. You can pull out the 1/3 right here, and the constant multiple rule right here. So you have 1 over x dx. So your answer would be 1/3 times the natural log of x plus c. Now, both of those follow directly from pulling the constant out from the and applying the rule. Nothing fancy, just make sure you're comfortable spotting the 1 over x in the different forms. Now, let's talk about exponential functions. Here, we have exponential functions. So let's say we have something like this, like e to the x dx. The integral of e to the x is e to the x plus c. Remember that for derivatives is very similar. But now what about if you have not just e to the x, but if you have e to the kx? So like e to the 3x, 4x, or something like that. What this says is that the rule is 1 over k times e to the kx plus c, but obviously k cannot be equal to 0. So this first rule is beautifully simple, just because it is e to the x. It's its own antiderivative, just like for integrals as well. So it's very similar, actually the same. That's one of the things that makes e so special in mathematics. The second rule handles the case where the exponent has a constant coefficient k. The antiderivative is the same exponential, but you divide by k out in front, and think of it as undoing what the chain rule would have done if you differentiated. Okay, so let's work through examples. Let me give you 2 examples. So let me give you another example right here. So now let's say we have 3 times e to the negative 0.2 dt. Now notice that the 3 can be pulled out, so I'm going to pull out the 3 e to the negative 0.2 t. And this, you don't have to do this every time. If you can recognize it, you can pull it out. But I'm simply doing this just so you can, so it looks just like the form that we have. So notice that for this particular problem, the k is the negative 0.2, okay? So if I do that, so this gives me 3, right, times negative 0.2 times e to the negative 0.2t plus e. Now, usually we don't leave this as a fraction, especially if it has a decimal. So remember that 0.2 is the same thing as 2/10 or 1/5. But if you divide it by 1/5, you have to multiply by the reciprocal. So this becomes negative 15 times e to the negative 0.2t plus c. Okay. So we have k is equal to negative 0.2, right? This is what I identify my k right there. And so I divide everything by negative 0. I divide it by negative 0.2, which is the same as multiplying by negative 5, okay? So now let's combine both rules. So integrals, sometimes we can mix both types in the same expression. So let's do one example that combines the exponential and logarithmic rules in one problem, just like we did in video 1, okay? So another example right here. So let's say that the integral of 2e to the x plus 4 over x dx. So if we rewrite this, we can write this as the integral of 2e to the x dx plus 1 over x dx. So this one is nice and simple. So we just have 2e to the x plus, this is 4 times the natural log of the absolute value of x, and then plus c. So we are done with this one. There are different application problems. We can do a quick application problem. This will be our last example for this section. So let me do, let's call this an application example. And we'll say that we have c prime of t is equal to 8 e to the negative 0.4t. And we'll say that c of 0 is equal to 5. Or sometimes you'll see this as lowercase, okay? It depends on the books, but we are trying to find like the capital C of t, which is the antiderivative of this. So we want to be able to integrate this. So to find, excuse me, to find C of t, we want to be able to integrate 8e to the negative 0.4t, which is equal. So now, for this specific problem, what I like to do is I like to identify my k first. So that's negative 0.4, which is negative 4 over 10, which is negative 2 over 5. Excuse me. So this kind of problem, again, it's pharmacokinetics problem. Excuse me. Where we're looking for the change of concentration in the blood to see the rate of concentration in the blood is proportional to the current concentration. So now we can integrate this. I apologize for my coughing, and I cannot really edit these videos, so I apologize. It stays here. So now let's integrate this, right? So C of t, this right here, we said that it was the integral of 8e to the negative. You can put 0.4t there, but when you bring it down, I like to write it either like this, divided by negative 0.4 times e to the negative 0.4t plus c, or what you could do, you could say this is 8 divided by negative 2/5 e to the negative 0.4 t plus c, which this is simply, since you have to multiply by the reciprocal, this would be 5 times 8 over 2 e to the negative 0.4 t plus c, which this gives us, so that's 4, that's 20, negative 20 e to the negative 0.4 t plus c. Now, there's one more thing that we have to do. We have to apply the initial condition. So we'll say that 5 is equal to, right, the initial condition is equal to negative 20 e to the negative 0.4 times 0 plus c. So this gives us that that positive 5 is equal, so that goes to 1. So negative 20 plus c. So in this case, the initial condition, it is 25. So now we have found the full form. C of t is equal to negative 20 e to the negative 0.4 t plus 25. So, and we are done with this problem. So we've applied the initial condition. We have found what the original formula, not equation, but equation was C of t. So we remember that whenever you see 1 over x dx, it equals to the natural log of the absolute value of x plus c. Don't forget the absolute value bars, and the natural log of e to the kx dx is 1 over k times e to the kx plus c. Divide by k, not multiply, okay? I will see you in the next video. Thank you.